Welcome and hello. This is a video exercise in HEC RAS. And in this exercise, I'm going to be dealing with the histograph tool as well as run through a few different simulations for sediment loading. So let's go ahead and get started. I got HEC RAS up on the screen here. I'm going to go File, New Project, and then navigate to the directory I want to save this project in. And then give your project a name and then click OK. Okay. All right. Let's start off by defining a geometry. So then after that, a flow, sediment data, and then we'll run the simulation. So click on River Reach, and then go ahead and do a single left click on your map here, and just keep doing little clicks to add some curvature to the reach, and then a double click to finish the reach off. I'm going to call this River A, Reach 1, and then click OK. Next, cross section. I'm going to define the downstream cross section first. So add a new cross section, River Station 0, and then I'm going to go ahead and just paste in some data from Excel. So I got it on my clipboard, paste, and then the downstream distance is going to be 0 because this is the downstream most cross section of the reach. Manning's end values, and then the bank station on the left is 100 and 250 on the right. Okay, so apply data. Here is a little diagram of what that cross section looks like. All right, I'm going to add a few more cross sections. I'll do the upstreammost cross section, then add some interpolated cross sections, and then save the file. All right, so options, copy current cross section. I'm going to just go up about 5,000 on the river station. Click OK. And then I need to add some distance here to the downstream length, as well as a little bit of elevation. I'll just go with 5 feet here. So this is a 0.1% slope. Apply data. Okay. Now let's go ahead and add a few more intermediate cross sections here. So within a reach, and then what I'll say here is every 250 feet. Okay, interpolate and close. That looks good for our geometry. I'm going to go File, Save Geometry Data. I'm going to call this Base, and then click OK. Geometry base file has been loaded to our list of files up here. Next up, let's go ahead and define some flow data. So for quasi-steady flow data, which is what we're going to be using here for a sediment transport model, I'm going to click on the button right here, View/Edit Quasi-Unsteady Flow Data. You can also just go up to Edit and then Quasi-Unsteady Flow Data Sediment. All right, so downstream boundary condition, I'll just set this to the normal depth, which is the slope of the channel, or the energy grade line to be specific, but the channel slope is a good approximation. All right, and then for the upstream boundary condition, I'm going to click on Flow Series. And then what I want to do here is just use entered table. So I'll manually enter the data, use simulation time, which means the flow data, the flow data is going to start at the same time as the simulation. And then right in this table here, I'll enter the flow duration in hours, computation increment, and the flow rate in CFS. So I have that on my clipboard. I'm going to Control V to paste. Let's see if that worked. Yes, so it pasted in. It's going to start off at 100 CFS. It's going to ramp up to 800 CFS for just 6 minutes, and then back down to 100 CFS for a number of hours. So if I click the plot button, okay, no values to plot. I don't quite understand that, but all right, so let me just go ahead and click Save. I'm going to go ahead and File, Save, Quasi-Unsteady Flow Data. I'm going to give it the title 100-800-100 just to help me remember what the range of flow rates is for this file, and then click OK. Also, for the temperature, I'm just going to set that at a constant 50 degrees Fahrenheit for the entire simulation, which is going to be for 24 hours. I'll just say 24 and 24. Okay, so that's good. Does that plot work? Also, no. Interesting. I think I might have to save it first. Let me go File, Save. Let me go to the flow series data and then plot. Okay, still no. Strange. All right. Anyway, let's carry on. We don't need any more flow data entry. We're all good there. But what I'm going to do a little bit later is come back to this histograph generator once I've assigned a sediment file. We really can't use that quite yet until we define the sediment. Okay, so I'm going to close that. And then for Edit Sediment and Data, here we go on the first tab. I'm going to go Initial Conditions and Transport Parameters. We have the river, we have the reach all set. The transport function, sorting method, and fall velocity method, I'm just going to use the default values there. For the depth, I'm going to say for each cross section, there's 5 feet of depth. Then I'm going to copy that all the way down for all the cross sections. For the left and right stations, I'm just going to use the bank stations. So that's quick and easy. And then for the bed gradation, I have to define that gradation here. The first thing to do is to create a gradation. So I'll just call it grade 1 and OK. And then I have it saved on my clipboard. So I'll paste that data in. And you can see the percent finer in that gradation curve right there. OK, so I'll click OK there. Now for bed gradation, I'll go ahead and make that assignment, and then I'll copy that down for all the cross sections. The next thing to do for the sediment is go over to the Boundary Conditions tab, and I'll select River Station 5000. This is the upstream most cross section of the river reach. And then I'm going to click on Rating Curve. So now what I want to do is set the number of flows to the flow load points to 2. That's fine. And then for the flow rate, remember it ranges from 100 to 800 from our flow data. So I'm just going to go 100 and then I'll say 1000 for the maximum. For the load, at the lower flow rate of 100, I'll say the load is only 500 tons per day. But then for the higher flow rate, I'll say that's 100 times more, which is 50,000. Okay, that looks good. Now it needs a distribution. So let's go ahead and do that. I'm going to go ahead and paste in a distribution for the low flow at 100 CFS. And then I'm going to paste in a different distribution for the higher flow rate, which has some larger grain size classes. Okay, does this plot button work? All right, looks good. Keep in mind there's no percent finer when you're actually defining the rating curve data for sediment. It needs to be like the percentage in that class. Okay, so I'll go ahead and click OK. File, save sediment data. I'm going to also just call this base. In case I make a change, I can call it something else, but right now I'll just call it base. Okay, and then I can close that. Let's go back to that flow data now and click on Histograph Generator. Without a real strong idea of what I should put for this threshold here in tons, I'm just going to guess something. I'm just going to guess 10,000 tons. That might be too much or too little. I'm not sure. But I'm going to use the sediment file rating curve and then the base, that's the sediment file. So with the flow data and the sediment data combined, it will know how often 1,000 or 10,000 tons of sediment threshold and then create a new time step every time that happens. So let's just go ahead and see what happens here. I'm going to go ahead and click this button down here on the bottom left, save quasi unsteady flow. And then now it's asking me for a file name. I'm going to call it 100-800-100 underscore and then 10,000 T, representing the 10,000 ton threshold for this histograph. Okay, so I'll click OK and then exit. So I believe that's been created. Let's go ahead and check it out. File, open. Yes, sure. And then here it is. It's the file name we just called it, or the title and then the file name. So let's go ahead and open that up. And then flow series has been loaded in here. So this looks like a unique flow file because there's no downstream boundary condition. I'll go ahead and click the flow series. And what it has is just a single value here representing a single time step. So what that tells me is 10,000 tons is too large. I'm going to go back and change that, and we'll generate a new flow histograph here, a new flow file with a different threshold. I'm going to go up to File, Open. I'm going to go back to my original, click OK. And then now let's go ahead and click on the histograph generator again. This time I'm going to make the load smaller. I'll just say it's 500 tons. And then again, I'm using the same sediment rating curve and the sediment transport file. Okay, so I'll click on Save, and then I'll give it a new name. This time it's going to end with an underscore 500T. That's just the way I'm doing it. Okay, looks like that's been generated. I'll go File, Open. Here's that file we just created with the 500 ton threshold. I'll click OK. I'll open up the flow series, and it looks like it's still too much. Okay, so 500 tons is still too much. So we need to do it again with a smaller threshold. All right, so File, Open. Let's go back to the original. Okay. And then again, click on Histograph Generator. So it's got to be less than 500. How about just 10? 10 tons? Okay, so save. I'm going to paste it in with an underscore 10T at the end and OK. All right, so let's go ahead and see what happened there. File, Open. Here's the 10. Hopefully we have some more than one record here in the time. Okay, good. So this is what I wanted to see. We start with a number of records here at 100 CFS, and then it begins to ramp up, and we should have a bunch at 800. Yep, here's 800. The duration is 7.5 times 10 to the negative 3, so that's very short. Of course, this is in hours. Let's see. Okay, so I got that at 27 seconds, just doing some math. And then, yeah, so as the flow rate decreases to 200 and then back to 120 and 100, then the time increments get a little bit larger. The flow duration is a little bit larger because remember, this is a constant 10 tons of sediment. All right, let's see. Can I plot this? Nope. Okay, still no. I'll go ahead and click OK. Let's go ahead and use this one. So I need to make sure to specify the downstream boundary condition again. And OK. All right, let's go ahead and create a plan and run the simulation and just see if it works. So I'll go up to Run, Quasi Unsteady, and then File, Save Plan. I'm going to call this Base, just BASE, base here. All right. So I'm using the geometry file, our one and only flow file. Actually, this is the flow file we generated with a 10-ton threshold per time step. And then the sediment data, only one of those. We'll go ahead and type in the date time. For the starting date, I'll just say the first day of the year, and then that will go until the next day. All right, so that looks good. One more thing I'm going to do for the output options, I'm going to change the level to 6, and I think everything else is good. So click OK, and then I will save that data and click Compute. Okay, so flow or time series data is not sufficient. I'm pretty sure I just need to extend the time period a little further. Let me take a look at our flow data real quick. So let's look at the temperature. Oh, I don't have any temperature data. Yeah, that'd be good. I'll just, oops, say 50 degrees. And then for the number of hours, I'll say 24 hours. Okay, so that should be sufficient. I believe that's what it was complaining about. Let me go ahead and file, save, close, and then let's go back ahead and run it. See if that was, no? Okay, I'm going to go back to the flow data once again. I know the temperature data is correct, so it must be in here somewhere. And what I'm going to do, just to be safe, is I'm going to go down to the bottom of the records here and just paste in. Oh, yeah, so it only goes to 23.4 hours. I thought it was full 24 hours. But I'm just going to go ahead and copy this record, paste, and paste one more for good measure. All right, I think we're beyond 24 hours now. So let's see if that works. File, save. I'm going to go ahead and close that. Then for sediment data, click compute. All right, looks like that was our problem. We're fixed now. And click close. All right, let's go ahead and look at some results. So I'm going to come up to the view menu and then sediment output. I'm going to take a look at the variable called mass in. Mass in is right here. If you're unfamiliar with what the definitions are, I will leave a link in the description to this page here. It has a alphabetical list of the definitions, the units, and then the actual name. So mass in, for instance, in units of tons is the total sediment mass for all grain sizes and so on. So that's what this is. It does break down by individual grain size classes as well. So that's why you're seeing this indent with the different grain size classes. So that's, I believe, available if you're using the output level 4 or above, but I was using 6. So that's definitely why I'm getting all this data here. Okay, at the top of the reach, we have River Station 5000. What I'm going to do is toggle off the total. And what we're seeing here is all the individual grain size classes. I'm going to click on this button here to give some different colors. And then I'm going to zoom in by just kind of dragging along here. Okay, so we have a range from 0 up to 3, and that's in tons. You can see in the middle of the simulation, this is where the flow rates really increase, and that's why the lines kind of get jumbled up because we have two different gradations for those two different flow rates. But if I wanted to see individual data, like individual grain sizes, I could go ahead and toggle some of these off. So red right there is the very fine sand. Here's the fine sand, medium sand, coarse sand. And these larger grain sizes we're seeing actually peak and increase right here. And that's because the higher flow rates bring in the larger grain size classes. But if I did the opposite here, let me toggle off everything except the largest and the smallest grain size. So very fine silt right here is just the opposite. Fine silt has a similar shape. So we have more mass at the higher flows, less at the lower flows, and then back up again. I'm going to check out the mass bed change cumulative. That's a different variable. That's this one right here. And as you can see, there's a large spike about 8 hours into the simulation. That's where the flows peak. This purple line at the top is the total, I believe. So let me toggle off the total. Okay, now we have the individual grain size classes right here. So you can see the labels. If I'm using the point bobber, which is the labels that you're seeing as I kind of mouse around. The top in gray there is MS for medium sand, and then next one down in red is the FS for fine sand, and then blue, this light blue here is the coarse sand, and then down below here we have some of the finer particles, I believe. And the reason why that's happening, if I just go back to the sediment data, and I click on the boundary conditions again, we saw when we clicked on rating curve that for some of these larger particle sizes, from fine sand up to very coarse sand, lower flow rates like 100, we have 10, 5, 0, and 0% of the total flow by mass is those four particle sizes. But at higher flows, 1,000 CFS, it's going to be 18%, 15%, 12%, 5% at the end. So that's why we're experiencing a lot larger grain size during the higher flows. Okay, so let me go back to the results real quick. View, sediment output. I click on mass in, but instead of time series, I'm going to click on profile. And this is the first time step. That's why we're not getting any, it's just a flat line. There's the simulation hasn't started yet. But if I click onto like the next time period, and then I toggle off the total, now I'm seeing the individual grain size classes after 28 minutes here. These are larger time steps at the beginning because remember it's low flow, and the flow file is based on a constant sediment, not a constant duration. Or actually, let's go ahead and toggle off all but some of the largest grain size classes. So let's go with coarse sand right here. That's in green. So this is after just 28 minutes. And our variable here again is mass in. Yeah, mass in. And then let's go ahead and advance to peak flow, which occurs at about 6.5 hours. Yeah, so you can see the time step right here is only about 27 seconds, like I said. So I'll click that on. And then, yeah, you can barely see the green line anymore because it's dwarfed by the amount of flow here at the larger size, the coarse grain size. Sorry, the coarse sand size. Now let me go halfway back, maybe to like 4 hours in. So this is, like, you can barely see that record as well. Let's go a little bit further to maybe 6 hours in. Okay. I don't have the flow rate with me right now. Here's 10 minutes before. So something I can learn from this plot is not only is the sand, this coarse sand that we have highlighted, most dense, and the mass coming in is proportional to the flow, more mass at higher flows, but also that it's settling because this purple line drops down right away. It doesn't go all the way across. So let me just keep these time steps still on, but but what I want to do instead is toggle off coarse sand and toggle on some smaller sizes like very fine sand. Okay, interesting. So yeah, very fine sand is way up here at the top. There's more mass in, and it stays in suspension. It doesn't settle out because it's a smaller particle, and that's why the lines stay suspended for the entire reach of from 5,000 down to 0. So let's go ahead and toggle on the next larger size. Okay, interesting. So I'm going to toggle off coarse sand. This is the fine sand. It looks like some of it settles, maybe about half of it settles down. About half of it gets deposited, and then the other half, it just remains in suspension until the end of the river reach. I'm going to do one more demonstration. And what I'm going to do here is change the flow data. So I'm going to go up to flow. For the file name, I'm going to go ahead and say new quasi unsteady flow file. And then the name is just going to be 100, very basic, a constant 100 CFS flow. What I'm going to do here is decouple the flow from the sediment load. So for the flow series, I'm just going to say 100 CFS, and that will be for an entire month. Plenty of time here. And then the computation increment, I'll just say is 1 hour. And then for the boundary condition at the downstream end, I'll just say normal depth. Type in the same slope as before. All right, file, save. I have to set the temperature data again. So we'll say it's 50 degrees again for an entire month of data. And okay. Now for the sediment, what I want to do is click on sediment. I'm going to call this load series. So I'm going to go file, save sediment data as. So basically making a copy. Instead of base, I'm going to call it load series. Click OK. And then for boundary conditions, instead of rating curve, I'm going to call it sediment load series. Now over here on the right, I'm still going to use two sets. Now I'm not seeing a flow rate anymore because it's independent of flow. It's just load per day. Let's go with 500 up to 50,000. And then I'm going to paste in the same data so it's constant. So it would be the exact same gradation. That looks fine. Now over here on the left table, I'm going to paste in the duration versus load. So remember, I have a constant flow of 100 CFS, and now I'm going to have a non-constant sediment load. that starts at 20 and then goes up to 1,000 CFS. And this is on a 1 hour time step. So it looks like I have enough data for, let's just make it 16 hours. Actually, let me extend this a little bit further so we have 24 hours worth of data. Okay, that looks good there. All right, so I'll click OK, and then File, and then Save Sediment Data. All right, so I'm going to go up to File, Save Sediment Data, and I'm going to use this Load Series Sediment Data when I create my new plan. So let's go up to Run, Quasi-Unsteady Analysis, Sediment. Now we're using the same base geometry, but this time we're using that constant 100 CFS flow with the load series, which is independent of the flow rate. So let's go ahead and save that as load series. Okay. And load series for the short ID as well. Let's go ahead and change the sediment output options. Okay, so that's still the same. That's good. And yeah, we're ready to go. Let me save one more time and then click compute. All right, so that ran. Looks like it was successful. Let's check out the results. I'm going to go up to view and then sediment output. As before, I'm going to go ahead and look at the mass in for my variable. Mass in right there. River A, reach 1. And then I'm going to change the mode to profile. Of course, this is a flat line because it's at the beginning of the simulation. But if I just go to the first time step here, and I'm going to also toggle off the total. All right, so here are the individual grain size classes at all the river stations from 0 up to 5,000. And this is interesting. So we have some of them are just flatlining across. That means they're small enough to not settle. They'll just float through the entire 5,000 foot long reach. And then some of the other ones, like this dark green one here. Where's dark green? I think that's fine silt FM. Actually, let me turn off the first profile. Okay. Yeah, I think the dark green is it's depositing a little bit, or not a lot. Red, there's no depositing. Pink, there's no depositing. Blue and black, no. But then this light blue and then this light gray are depositing most of their sediment over the course of the total reach. I'm going to go back to the sediment data and just recall when I specified that max flow. So sediment time series, I forgot what I put here. So this is the 8th hour, it looks like. Yeah, the 8th hour, I have 1,000 tons, not CFS, 1,000 tons. So I'm going to toggle off the first hour and then go up to the 8th hour right here. And now the mass in tons is a lot more. We're on the scale of hundreds of tons for these different grain sizes. And just out of curiosity, I'm going to change the mode back to time series here and then go at the top of the reach and then see, yeah, that's cool. So right here at the 8th hour, this is where all of the individual grain size classes peak because that's what we told it to do when we specified the time series load data in the sediment data file. All right. Well, anyway, I'm going on long enough. What this exercise did was it showed how to demonstrate sediment flow in a single reach in HEC RAS. We used the histograph tool to set a boundary condition so that our flow rate had a constant amount of sediment for each time step, and the time duration of each time step was variable. Then we had the opposite situation where we used a constant flow rate and then had a time series boundary condition to set different amounts of sediment load over the course of this simulation.